8.7. Continuation of Chapter 8. This is the second to the last section in Chapter 8. This is going to be a somewhat new idea. So this is novel when it comes to the content itself, but it's going to be built off of some stuff that we already understand pretty well. So everything we've been talking about so far in terms of vectors, angles, magnitudes, and stuff like that, trigonometry of the complex plane. So what we're going to do is we're going to take that a step further, and we're going to introduce the complex plane and understand it instead in terms of angles and distances. So we're going to be switching what's called coordinate systems. So we are used to working with a coordinate system that's rectangular in nature, and this will be the first time, I think, in your academic life that you're going to be switching it out for something else. So this is going to be switched out for polar. So polar is another way of measuring or position. So tracking location. So we can think in terms of rectangular position coordinates, so horizontally and then vertically. Now we're going to think of how far away and at what angle instead. So how far away versus how far away and what angle versus left and right, up and down positions. So our polar coordinate system. So it's based on a point called, so it's no longer going to be called the origin. So the reference point in the Cartesian rectangular coordinate grid is called the origin. In polar coordinates, we call it the pole. There's a single pole, and it's analogous to the origin, only up to a certain point. So, and we'll see why. And then we're going to have a ray. Ooh, I don't remember what that one's called. That one's just called something axis. That's the, I'm guessing the polar axis. Yeah, polar axis. So I'm just cheating and I'm reading ahead. I'd forgotten about that. So we have a pole and we have a polar axis. So it's only 1/2 of the x-axis. So it's in the direction of the positive x-axis. So let me draw that. So we think of a point and then a single 1/2 of an axis array. So we're going to call this R. So it's literally one reference point, and we're going to think of it as how far away from that point, and that's the number R. So we're measuring distance away from the point, and then we're also going to talk about a rotation angle, theta. And we could think of, let's say this is 1 radian, 2 radians, and so on. And of course, mathematicians always think in terms of radians instead of degrees, and these circles are terrible. But whatever. 3 radians. And before I butcher another circle, we'll stop it there. So 1, 2, 3, and it keeps on going. So we think in terms of some distance and some angle. So we could think of this as pi over 2 radians, 3 pi over 2 radians, but we normally don't draw those at all. We'll have grid lines, but we're not going to have axes other than just the polar axis. So I'll have a grid line over here, grid line here, and these grid lines go radially. So if that's pi over 2 and 3 pi over 2, we can think of this as pi. But we can do this in thirds. Pi over 6, which actually that's 2 pi over 6. Pi over 6 is here, and keeps on going. So another 1/3, another 1/3, another 1/3 is pi, another 1/3, another 1/3, and so on. So another 1/3 and a final 1/3. So it looks like a spider web the way that I drew it, but we think of them that way. So that's the way that we think of the polar grid. It's a circular grid instead. A polar and a circular and radial grid instead of. So that's different. This is polar, and then we think of a Cartesian rectangular grid with a bunch of dotted horizontal and vertical lines. Let's say that's 1, -1, 2, -2, say 1 again, but vertically, 2 vertically, -1 vertically, -2 vertically. So we have a rectangular grid, and it should be obvious now what we mean by rectangular. So rectangular, we're literally meaning rectangles. It's rectangular in shape for the grid lines. Polar is circular and radial in shape. So it's a curved spatial coordinate system. So it doesn't mean that space is curved in this situation. It's still the same flat plane that we're talking about. we're measuring coordinates along curves instead. So circular curves for a different radius, and then these radial lines for a different angle. That's polar. So to change between rectangular and polar coordinates, we use these equations, which we are very familiar with. X equals to a radius times cosine of an angle. Y is equal to a radius times sine of the angle. And those are coming from sine is y over r, cosine is y over r. So we're no longer thinking of just the unit circle. Now we're going to think of r as a variable, so we're going to change for different radii. So a different radius, so a variable radius, that is. R squared is still x squared plus y squared, and then tangent of theta is equal to y over x. That's how we change back and forth between rectangular and polar coordinates. That's how that's done. So we'll keep on going. Example number 1. Plot each point in the polar coordinate system, then determine the rectangular coordinates of each point. So that's in polar. So polar, P, 4, 135. Think of this as another vector with a modulus of 4 and an argument or an angle of 135 degrees. So we're going to graph that point. We want a modulus of 4 and an angle of 135 degrees. Modulus of 4, that's 1, 2, 3, 4. This one's 5, that far out. So notice how they put x and y coordinates on there? Not supposed to. They're only supposed to put one positive axis for r. But whatever. They just broke their own rule. So their own rule said it's only a polar axis, which is usually drawn in the direction of the positive x-axis. Well, what we're trying to do, though, is we're trying to translate back and forth between polar and rectangular, so they're fine to do that. So r is 4. R4 by itself, or r is 4 by itself, is we're talking about this circle in particular. And if I leave it like that as a relation, the full circle, that is r equals to 4. That's the equation r equals to 4 in polar coordinates. So if you remember, if I set x equal to 4, that's a vertical line that crosses the x-axis at 4. If instead I set y equal to 4, that's a horizontal line that crosses the y-axis at 4. So in polar coordinates, if I set one of the variables r equal to 4, it's a circle, not a straight line. So that's kind of cool in polar. An equation like that, r is equal to 4. That's a circle. It defines a circle. And what it literally means is find the circle with a radius of 4, centered at the pole. Not the origin, but centered at the pole. Okay, so we're looking at that circle again, radius of 4, but we're 135 degrees out from the polar axis. Polar axis is the positive x. So 135 degrees. The way they have it here is I can't draw it, so 135 is 45 degrees after 90, so that's this line. So I'm going to draw this line, by the way, and that's the line theta equals to, not pi over 4, 3 pi over 4, which is 135 degrees. So if you set an angle equal to a constant amount, it's a line, and it's a line from the pole a certain angle out, so whatever the angle is. Okay, so we're talking about what point? This point. That is 4, 135. And we're done. So then, well, we're done with the plotting of it. So that's the very, very first set of instructions. What's the rest of it? Determine the rectangular coordinates of that point. So that was A. There's a B, I guess. And there's a C. Okay, so I want the rectangular coordinates. So if r is 4 and 135 is equal to theta, then how do I find the rectangular coordinates? You can think of this as a, what's it called? As a complex number, RCIS theta. And you wouldn't be wrong to do it as long as you just changed it back to a set of coordinates. So we want coordinates, not a complex number. But they happen to be kind of the same thing. They're analogous to each other. They correspond to one another. So there's a relationship that I can change a complex number to a coordinate point, so a set of coordinates. So think of this as RCIS theta, and that is 4CIS 135. 4 and 135, we should know this. Square root of 2 over 2 plus I square root of 2 over 2. Distribute the 4. Negative 2 square root of 2 plus 2i square root of 2. If you distribute the 4, those 2's reduce the 4 to a 2. Okay, so that's a complex number, and they don't want this as a complex number. They want this as an ordered pair. So how do I change that to an ordered pair? So my answer is negative 2 square root of 2, 2 square root of 2. You disregard the I. The I just means that that's the y coordinate. This is what they want. So that's the mathematics for getting that. And if you understood the previous notes for 8.6, then that's how you would do it. The other way you would do it is you'd use these equations. So let me use those equations. Those equations say x equals r cosine theta, which is 4 cosine 135. I wrote of 135. There we go. 4 cosine of 135. You use the what's it called? The unit circle. Negative square root of 2 over 2. So negative 2 square root of 2, which is literally the x coordinate that I wrote over here. So it works. Why does it work? Because the CIS function is cosine plus I times sine. Your x coordinate is the cosine one, so cosine and cosine, same thing. So that's why the rule works the same. So CIS is perfectly fine if you want to use it that way. Just make sure to know that you have to write it as a point with x and y coordinates. Don't leave it as a complex number. That would be wrong. And then of course, y is equal to r sine theta. So that's 4 sine 135. 4 square root of 2 over 2, which is 2 square root of 2, which is exactly what we got. So that's two different ways to get that done. Number 2. So we have negative 3 pi over 6. Plot it first and then find the coordinates. So let's plot it. How do you do negative 3? That's weird. So negative 3, you would start it just the way you normally would. So negative 3, draw that on the, so we'll draw 3, right? So 1, 2, 3. 3's here. So 3's there. So there's no disputing that's 3. Where's negative 3? Negative 3's back here. So what does a negative do? Negative rotates it back to the other side of the pole, 180 degrees away. Right? So if you want negative 3 pi over 6, well, if you were at 3, pi over 6 is just a rotation up this way, and that would be this point. So pi over 6 from negative 3, you rotate at the same angle, pi over 6 this way. They're mirror images of each other. So it's along the same line, 180 degrees apart. They're just negatives of each other, 180 degrees apart. So this is the point that we want. So let me erase all those others to hide my work and make it as if I had actually known that all along. So that's the point that we want. This one is negative 3 pi over 6. So maybe that makes sense, maybe that doesn't. If you change it to rectangular coordinates, it should coincide with what we got over here. So maybe you could do the rectangular coordinates first. And to do rectangular coordinates, same idea. This is 3, negative 3, that is, CIS, pi over 6. So this is negative 3 cosine pi over 6 plus I sine pi over 6. Negative 3 square root of 3 over 2 plus I times 1/2. You should know your unit circle. Let me double check before I embarrass myself. I should know my unit circle. So yeah, pi over 6 is 30 degrees, sine of 30 is 1/2, cosine of 30 is square root of 3 over 2. So that's a 2, by the way. That doesn't let me fix it. So distribute the 3, or the negative 3. Negative 3 square root of 3 over 2 is the first coordinate. So I'm going to go ahead and cut straight to coordinates. Comma, negative 3 over 2, no I whatsoever. Hopefully that's okay with you guys. And yeah, notice how they're both negative. That means we're in the third quadrant, so that's consistent with what we drew earlier. So then we'll move on to letter C. So the point R is 2 comma negative pi over 2. So radius of 2, so 2, 1, 2, 3, 4, 5. So radius of 2, so we're on the circle with the radius of 2. And an angle of negative pi over 2. Negative pi over 2 is here on this line. So we're talking about this point. 2, negative pi over 2. So just think of it as an angle, negative pi over 2. So instead of rotating pi over 2 counterclockwise, you're rotating clockwise now, is how that works. So that's the point. So that one's an easy one. What would that be in complex algebra, or on a complex plane? That would be negative 2i. Hopefully you agree. I mean, well, it's also obvious what that is rectangularly, 0, comma, negative 2. So I don't even have to make the complex appeal, or appeal to your understanding of complex numbers. So we could just think of that as 0, negative 2. That should be obvious. So there's that. I'm not even going to check it using the equations. That one's easy enough. So that's it for number, what was that, example 1? Yeah, that's example 1. We're not going to do too much from here. It's just a bunch of stuff like this. So plotting points we need to be familiar with. What else? Going backwards. If they gave, or let's see. Oh, I see what this is. This is kind of interesting. Determine the following. For number 2, 3 other pairs of polar coordinates for the same point, 5, comma, negative 110 degrees. So I think what they're trying to illustrate here is the idea that unlike in rectangular coordinates, you can write a point in polar coordinates multiple different ways. So let's see, 5, negative 110. So a radius of 5, an angle of 110 degrees. 110 degrees negative looks like this, let's say. So negative 110 degrees. And 5 means it's 5 out this way. That's the point we're talking about. So they're asking 3 other pairs of polar coordinates for that point. So in other words, 3 other ways that I can express that point. So what's another way? I could think of one right away. We're going to say 5 again. But instead of negative 110 going clockwise, let's go counterclockwise. What would negative 110 be the same as going clockwise, or counterclockwise, sorry. So negative 110 from 360. So 360 minus 110 is how I want to do this. This is the same thing as 260 this way. Oh, and I put 100, my bad. 250 this way, my bad. So, because I don't know how to subtract. I was using a calculator, by the way, which I didn't need to use a calculator. That one's easy. So 250 plus 110 is 360 is how I found that. So 5, 250. So I found 1. They want 3. I need 2 more. So what's another way to find 2 more? So let's think of it this way. Let's try this angle, which is 180 degrees from that other angle. So I'm going to make it a straight line, so that way there's a distance of 180 between that point. And let's say this point out here, this one right here is 5, and what would that be? It's 90, 110 is 20, this would be 70 degrees, right? That's not the one we want. The one I want is 70 degrees, negative 5 as a radius. So negative 5 means it's going to get rotated 180 from there. Does that make sense? Negative 5, comma 70 would get you to the same place. What's another way? So let's keep it at negative 5. And instead of a 70-degree angle, we go backwards. Well, that's going to be tough to think of. So if I'm at negative 5 means this way. How far this way? So I want this angle from here all the way this way, up to here. Because negative 5 means I'm here. So if I'm starting at negative 5, that's there at that negative 100 or positive 180 that way. And from there all the way back that way is what I want to rotate. And it's negative because I'm going clockwise from a negative. That would be 70. So 360 minus 70. And I believe that's 290. So negative 290 degrees. Because then 70 degrees past that would give me a negative 360. And that's weird. That's hard to find 3 more. So this one obviously is easy to graph. This one was easy to find just by going backwards. This one I needed to think a little outside the box. And this one was thinking way outside the box. A little tough. But those are 3 other ways to do it. Okay, so what they're going to give here, these are in rectangular coordinates. So rectangular coordinates of those 2. Find 2 pairs of polar coordinates. So good, they're only going to make me find 2. So I need to find r, and I need to find theta. And for that I need those equations. R squared is, so you could do r squared or you could do r, is square root x squared plus y squared. 6 squared minus 6 squared of 3. That's plus negative 6 squared of 3 squared. Because it's x squared plus y squared. And if it's negative, the negative goes inside the square. And that is square root 36 plus 36 times 3. Negative goes away. So then it's going to be 2 square root of 36. And that is 12. That should be 12. You can double check. 36 plus 36 times 3 is 4 times 36. 4 comes out as a 2. 36 comes out as a 6. 2 times 6, 12. So that's pretty simple. So then r is 12. What's theta? That one's a tough one. Theta looks like, you could put in 2's in there if you want to think of it. That's a 1/2 and a negative square root of 3/2. So positive 1/2 for cosine is 60 degrees, or 300 degrees. 300 degrees is what I'm guessing. Alright, so let me graph that. So it's 6, negative 6 square root of 3. So 6 is not that far out. So that's in the fourth quadrant for sure. And what angle is that? So then you're going to have to take inverse tangent of, you take the y coordinate, negative 6 square root of 3 over 6. And disregard those 2's. You don't need those 2's. That was just speculation, and it led me to the right answer though. So then that's going to be inverse tangent negative square root of 3. And if you do inverse tangent of negative square root of 3 into the calculator, you're going to get negative 60 degrees. Negative 60 degrees is this. But what is that between 0 and 360? 300. So theta is 300. So that's the same thing as 300 degrees, is how that works. So then we found one. 12, 300. Let me give another. 12, negative 60. Those are freebies, and that's all they wanted, 2. That's an easy way. 300 is the same as negative 60, and that's because of these right here. So I'm going to use both of those. That's not cheating. That still works. So that's it for letter B. And that's it for number 2, by the way. So last thing that we need to know how to do is example 3. That's all I'm going to give you homework on, and that's all I'm going to test you over when we test over chapter 8, which will happen next week. Probably at the beginning of the week, like due Tuesday or Wednesday. Like I did the last time, it was due a Tuesday ago. So nothing this week because it took us 2 weeks to do chapter 4 if we're in dual, by the way. So I'm talking to my dual students because dual students have to still take tests. So there will be a test for this for dual students, not for pre-AP. So anyway, example 3. So for letter A, y is equal to 2x minus 4. That's a linear equation, which I can already graph that no problem. So sketch its graph is going to be the first set of instructions I'm going to go ahead and follow, because the graph of that is easier in rectangular coordinates. Y is equal to 2x minus 4. So you can go ahead and cheat that way, because there's no way you're going to be able to see the polar equation and know intuitively how to graph that. So a straight line in polar equation that's off of the pole or off of the origin isn't easy to figure out mentally. So you'd need maybe the help of a graphing calculator for something like that. It's already in rectangular coordinates. Go ahead and graph it that way. So this is a straight line that crosses through the y-axis at negative 4. This is negative 1, negative 2, negative 3, negative 4. And yeah, that's still the same x and y coordinates. So if you have a point that's on the y-axis, then it's still a distance of 4 away. So there's no inconsistency there. So there's a point there. This line has a slope of 2. So in other words, if we move to the right 1, the y-coordinate's going to change by a positive amount 2. So if I do that twice, you're going to end up here at 2, 0. So you can double check that, but that's easy stuff. That's Algebra 1, freshman level stuff and below freshman. So That's the equation that we want. This is the same thing as y is equal to 2x minus 4, but we're going to go ahead and give an equivalent expression. It's going to look really ugly too. Straight lines in polar are hideous. So what does that look like, and how do I figure that out? We're going to use those equations that we had earlier. Y is equal to r sine theta. X is equal to r cosine theta. And I'm going to plug those in directly for the x and the y coordinates. So instead of y is equal to 2x minus 4, that's r sine theta is equal to 2r cosine theta and then minus 4, which I could distribute the 2, or not distribute the 2, sorry. That's just 2r cosine theta and then minus 4. I'd like to solve for r, and maybe the way to solve for r in this case is division. Divide r into everything. That's as long as r does not equal to 0. So we're considering points that are not at the pole, and that's perfectly fine, because if you take a look at the solution, none of the points on that line include the pole, so the pole's not a solution to that, so I don't have to worry about this not equal to 0 situation, so that's no big deal there. So in this case, these r's cancel. You're left with sine theta is equal to 2 cosine theta minus 4 divided by r. So now normally in polar coordinates you don't necessarily have to pick and choose which is the independent and which is the dependent variable. Specifically in algebra, y is the dependent variable, x is the independent, and we always solve for y in terms of x. Here it doesn't matter. It's harder to solve for theta, so I'm not even going to bother. It's easier to solve for r, so that's what we're going to go ahead and try. So I'm going to try to solve for r. So I want to isolate that r term, so it's going to be 4 over r on this side, 2 cosine theta minus sine theta on this side. Then you're going to cross multiply. If you cross multiply, you get r is equal to 4 divided by 2 cosine theta minus sine theta. And there's our equation. That's what's graphed here. And like I said earlier, there's no way you could have looked at that equation for r. In this case, that's r of theta. So there's no way we could have looked at that equation for r and been able to graph that no problem intuitively. So that's why I graphed it ahead of time as a linear function. X squared plus y squared is equal to 25, which I want to go ahead and make you think about. X squared plus y squared is equal to 25. We've seen that before. Just for a little bit. Chapter 2, I think it was. Chapter 2, we went over circles. That's a circle. Think about it. Look at it really quick. It's a circle with a center where? What's the center of that circle? And you should know that it's the origin. What's the radius? 5. It's 25. So here's what I mean by that. Change this to polar. X squared plus y squared is r squared. That's a freebie. Equals to 25. And that's it. That's the polar form. That's done. That's what they want. So for each rectangular equation, give the equivalent polar equation. And that's it. Because x squared plus y squared is equal to r squared. So r squared is equal to 25. And that's it. So how do I graph that? Or that's actually not done. That's not it. Take the square root. R is equal to 5 is the other way to write that. So r equals to 5. So 1, 2, 3, 4, 5. We're talking about this circle out here. And I got to graph a circle, and I suck at graphing circles. Start here. Nice thing is I'm just outlining a circle that's already there. And not even that can I do on my own. And that's the best I can do. R is equal to 5. And this is all that we're going to be required to know for this particular section. So we're going to go ahead and stop here. I'm not going to go over these special ones. We're not going to have time for it. Or I'm not going to make time for it. So not really important. You won't see that in calculus too much. Maybe if you take your second semester, third semester calculus when you go over parametric and polar again. But no, you'll worry about it then. And then it's going to be so much more complicated than just this. And you're not going to need to know this stuff. Your professor should go over all this stuff all over again with you guys. That shouldn't be too hard. And if you make it to your second semester, This is not going to be the hardest part about that course. So you'll be fine. So we'll stop here.